Hi, welcome. Yeah, in this video we are going to, this is part 2 of our exploration of Sylows theorems. Apparently this Sylow dude had a lot of theorems, so this is our second exploration of these theorems. So far, here's what we know. Here's what we've been trying to establish, that suppose suppose that G is a group, right? Suppose that G is a group, and suppose that the order of G, right? Alright, Java, no need for updates. So, suppose that the order of G actually equals to P to the alpha, alright, times M, and here the GCD of P and M, which from now on we're just going to write as GCD of P and M equals to 1. That is, P and M have no facts in common. Whenever this is true, the claim is that there exists some subgroup H of G, right, H subgroup of G, and this H has some interesting property. The order of H has to equal to P to the alpha. That is, there exists a subgroup of order P to the alpha, right? P is being taken to be a prime, of course, and alpha is being taken to be greater than or equal to 1. Alright, so, well, at least that's what we're assuming for now. Alright, so the prime part is correct. Whether alpha is greater than or equal to 1, we're not sure, but let's say alpha is a non-negative integer, right? Let's put it that way. So, actually, yeah, let's just say alpha is an element of the set of integers that are greater than or equal to 0. Okay, so yeah, I mean, how do we tackle a problem like this? So the major question to really think about is, well, how do we prove that a group has a certain order? Let's start from there. How do we prove that a group has a given order? Right. That's an important question to think about. In what ways can we do this, right? So how do we prove it? Which means we're not looking for one way, we're probably looking for multiple ways. So one obvious way to prove that a group has a certain order, so let's maybe make it more specific. How do we prove that, okay, I'm not gonna be writing all this stuff. How do we prove that a group H, right, has a group H, let's say, or let's use another name. How do we prove that a group M has order, let's say, R? How do we prove that a group M has order R, right? How would we be able to show this sort of thing? Well, what methods do we have? One method appears to be to uh, one way to do this is to find, alright, how do we prove this? One way to do this is to find some little m element of big M such that the order of the element equals to R, right? So, first of all, why is this convincing? So, is this a viable strategy? Let's first examine why it may be a viable strategy, and then let's examine other possibilities as well. So, that's one option, right? These are potential. We need to proceed systematically in this exploration. So, these are potential. Maybe let's put them in purple. These are potential strategies for answering the question, how do we prove that a group has a given order, right? Because ultimately we want to prove that a subgroup H has a given order, that G has a subgroup H of order P to the alpha. So we may ask the general question, well, how do we prove that any group has a given order? So far, one idea we are considering is, well, okay, suppose we're, okay, enough with the colorful stuff. So suppose we're able to prove that this group M has some element, well, let's call it little g. Suppose we're able to prove that there exists some, yeah, suppose we're able to prove that there exists some little g element of M such that order of G equals to R. Would that imply that Now, maybe we're asking the question a little differently. Maybe let's ask this question instead. How do we prove that there exists, right? How do we prove that there exists some subgroup L of M such that order of L equals to, let's say, R, right? Right. And the idea is, well, maybe one thing we can do is, one strategy is, let's find some little l, let's find some little l element of M such that order of L equals to R, right? So why is this valuable? So suppose that we actually found some little L element of M, of the group M, right? Little L element of the group M, right? Such that order of L actually equals to R, right? Why is this useful information? Let's consider the following collection of objects. Consider this collection. We're gonna call it H, right? For lack of better letters. Well, they're better letters, but we're lazy. So, okay. L to the 1, L to the 2, all the way up till L to the R minus 1, right? Let's consider this set here, H. Question. First of all, is H a group, right? So, I mean, how many elements does H appear to have? Does it appear to have R elements? Well, how can we tell if H actually has R elements or not? Well, one thing to verify is that, I mean, could we perhaps verify that none of the elements in L are the same element? All of them are distinct. That is, for all, if I does not equal to J, then is it true, does L to the I equals to L to the J is the question, right? So, I mean, if I does not equal to J, well, we may as well suppose that, could we suppose that I is less than J? If that's the case, this is I, L to the I. If that's the case, since L is an element of M and M is a group, can't we say that L to the I has an inverse? So consider L to the I inverse times L to the I. We multiply it on both sides of the equation. So then we have L to the okay, errors. Okay. And then we consider L to the I inverse multiplied by L to the J, right? We're multiplying our equation on the both sides to the left by L to the I inverse. What does this give us? This gives us, well, what's L to the I inverse times L to the I? Does that give us the identity? What about the left hand side? What does that give us? Does that give us L to the J minus I, right? So if J is greater than I, isn't J minus I, right? I and J, of course, are being taken to be some integers. Isn't J minus I some non-zero integer, element of Z, such that J minus I does not equal to 0, right? So, and actually, we're picking I from their natural numbers, actually. They're natural numbers. In fact, we must emphasize that. Natural numbers, and they're not equal to 0. So the question becomes, well, each of the elements L to the J minus I, right? So the order of L was, what was it taken to be? R, right? Well, now, aren't we saying that I is less than J is less than, well, less than or equal to 1 in this case, and less than or equal to, what was the order of L? R, right? Right. if we're picking I and j over here, right? Well, I mean, what's the order of L? Order of L was R. So, and we're saying that I is less than j, and j, whatever j is, has to be less than R, and I can be at least 1, right? At least 1. And so, if that's true, then can we also say that j minus I is less than R, is the question, right? If this is true, if I is less than j is less than R and is right between 1, can we say that j minus I has to be less than R? If we can say that, right, and we're saying that, well, which element do you know of, right? So, question, if this is true, if j minus I is less than R and order of L equals to R, can we ever claim that, is it true that L to the j minus I can equal to the identity, right? If L to the j minus I can equal to the identity, and we're saying that we found some element less than R such that L raised to that element, namely j minus I, gives us the identity, right? Is this contradicting the fact that R is the smallest natural number such that L raised to the R equals to 1? If this is true, then how can L to the j minus I ever give us the identity is the question, right? So maybe this can happen, all right? If this can't happen, what's that telling us? Isn't that telling us that if I does not equal to j, then L to the I cannot equal to L to the j, because if L to the I were equal to L to the j, wouldn't that also mean that 1 equals to L to the j minus I? But how can L to the j minus I equal to 1 if the order of L equals to R, and j minus I is being taken to be less than R? So from here, can we say that if I does not equal to j, L to the I can never equal to L to the j? Okay, so we've gotten this set of ours. We've gotten all. We've shown that. Have we now successfully shown that all the elements of H that we've written here, L to the 0, L to the 1, L to the 2, all the way till L to the R minus 1, are each distinct? If that is true, what does that tell us the order of H has to be? How many elements are in the set H? Do we have R elements in the set H? Okay. If we have R elements in the set H, okay, now the next question to think about is this H a group? Right? That's the other question to think about, is because we're almost there, isn't it? Remember, what are we trying to show? We're trying to find some subgroup of M that has order R, right? So we found an element of order R, and we've used it to generate this set of elements, L to the 0, L to the 1, up to L to the R minus 1. And we're asking, well, our hope is that maybe this H is going to give us a subgroup of M that has order R. So far, the set has order R, but is it a subgroup? How do we prove that something is a subgroup? Right? Isn't the first step proving that it's a group to begin with? So, particular, well, I mean, do we have associativity? Is it associative? How do we prove that something is a group? Right. So, for instance, is it associative? Is multiplying a bunch of elements in L associative? In H associative? Well, aren't the elements of L being taken from M, right? Oh, maybe wiser might be to start with closure first. Okay, let's ask this: is it closed? Is H closed? That is, do we want to start with closure? Sure. Why not? Is H closed? If we got some L to the I, where I is one of these powers, 0, 1 to R minus 1, and multiplied by some L to the J, where J is some power between 0 and R minus 1, what's the product going to give us? Is it going to give us L to the I plus J? Okay. Well, if you consider L to the I plus J, right? So, I mean, is I plus J going to be necessarily, is L to the I plus J necessarily going to give us some element in the set H, right? Is the question. Well, that would be closure, right? Is that if you multiply two things, you get something in the set. So, would this give us something in the set? Well, I mean, don't we just have two possibilities? Suppose I plus J is actually less than R, right? Wouldn't that mean that L to the I plus J is some element in H? Okay. What if I plus J is greater than R, right? Right. Wouldn't just let's say L plus I is greater than J, right? What if we just considered, well, doesn't that mean that, how do we put this well? Right, suppose L to the I plus J is greater than R. Doesn't that mean that L to the I plus J equals to L to the R times I plus J minus R, right? Would you buy this idea? We've just, okay, I mean times L, of course. So this is what we have now. Would you buy this idea that actually L to the I plus J equals to L to the R times L to the I plus J minus R, right? Well, what's L to the R? If the order of the group is, if the order of L is R, what's that telling us? That tells us we have L to the I. Is that telling us that we have L to the I plus J minus R? Okay. Suppose this is greater than R. Don't we just, again, pull out the L to the R from it until, couldn't we just do that until we get, make sure that we have L raised to some power alpha where alpha is less than R, and within that guarantee us an element within that guarantee us an element in the set H, right? So would you buy the idea that actually H is closed, right? See if you could prove that H is closed given this information. So if H is closed, all right, also the other question is, all the elements in H, are they elements of M? If L was an element of M and M is a group, is multiplying L by itself a bunch of times still going to give us an element of M, given that M is a group and groups are closed? Right? So can we conclude that every element of H is also in M? That is, can we conclude that H is a subset of M? Okay? If H is a subset of M, then, and M is associative, can't we say that multiplying a bunch of elements in H is also going to be associative? So let's see if you buy associativity from here. Okay, we have closure so far. Do we have the identity element in here? What about L to the 0? Is that the identity element? What's L to the 0 multiplied by any other power? Doesn't that just give us L to the I? Okay, so maybe we have the identity element here. If we have, do we have inverses? Well, let's check that out. What's L to the I inverse, right? If we pick some I in J in H, what's L to the I inverse? What does it mean to find the inverse? Aren't we looking for a number such that when we multiply it by L to the I, we get the identity back? Well, what about, could you guess such a number? What about, what do you think you're going to multiply by L to the I in order to give us the identity? Right? How about L times negative I? Well, sure, what would that give us? L to the I minus I, which equals to what? L to the 0, which equals to 1. Well, now you may be saying, well, okay, fine, but negative I was never one of our powers. So how do you know that L to the negative I is actually an element of our set H? So maybe let's check something else. What about if we multiplied L to the I by L to the R minus I? Right? What would that give us? Well, if I is less than R, right? If I is less than R and at least 1, isn't R minus I, right? Maybe let's multiply first and then deal with the technicalities. What does this give us? Then this give us L to the R minus I plus I. What is that? Isn't that L to the R? Okay. What's L to the R? If the order of L equals to R, doesn't that mean that this is the identity? Okay. So, but the question may be still again, how do you know that L to the R minus I is an element of the set H? Well, if I is less than R and I is at least 1, can't we say that R minus I is certainly less than R and is certainly at least 1? Right? Let's see if you buy this idea. If you buy this idea, then can't we say that the inverse of L inverse, L to the I inverse is just equal to L to the R minus I, right? So can we claim that we have inverses? All right. So if we have the identity, we have inverses, we have associativity, it's closed, isn't that just a group? So what are we saying here? We're saying this thing, if we found an element L of M, whose order was actually R, we're able to generate this set here we're calling H, which has elements L to the 0, L to the 1, L to the 2, all the way up till L to the R minus 1. And what else are we saying here? We're saying H is a group. H is a group, okay? Order of H equals to R, alright? If H is a group and order of H equals to R, and H is a subset of M, aren't we saying that H is a subgroup of M such that order of H equals to R, right? Isn't that the idea, right? So does it make sense to say that if we want to prove that a certain group has a subgroup of a given order, does it make sense to say that perhaps the best, one of the ways, not the best, but one of the ways to do that is to find an element in the group that has the order R, right? So and this is what it's claiming here, because ultimately Sylows theorem is asking us to find, well, for any group, want to find some subgroup that has some order. In this case, order is p to the alpha. And so we're saying, well, how do we show that a group has a subgroup of a given order? How do we prove that there exists some subgroup L of a group M such that order of L equals to R? Well, one way to do it is find some little l element of M and show that the order of little l equals to R. That may be a possible strategy to solving a problem, to finding a subgroup of order p to the alpha. But in this case, we're starting a little general, just asking, how do we find a subgroup of any given order, right? So that's one potential approach. Whether it works or not, we are not so sure. But the question becomes, well, is there another approach? Could there be another way in which we could prove that a certain group has a subgroup of a given order, right? Could there be another way, right? How else do we prove that we have a subgroup of a given order? Well, how about this approach, right? So we know that, again, so if you haven't learned this, please go check out our videos on Lagrange's theorem. So it's a playlist. Just type in exploration of Lagrange's theorem in YouTube and you'll find them. This is Lagrange's theorem. Lagrange. Let's write him well. His French name may be confusing. Lagrange's theorem. This is supposed to be an R and A. G. Lagrange's theorem. Okay? So it's, just type in exploration of Lagrange's theorem and you'll be able to see this theorem and how we proved it. And the idea was, look, if G is finite, if G is a finite group, we know certain things. We know that any subgroup H of G has the following property. The order of H must divide the order of G. Right? Again, this is not something you should take on faith or whatever. Just if you're really confused by it, please check out the exploration of Lagrange's theorem. But this is what the theorem claims, that if you have a finite group, any subgroup of it, the order of any subgroup must divide the order of the group if the group is finite. Well, okay, given this information, can we figure out perhaps a potential way of proving, of maybe showing that a group, or let's say a group or a subgroup has a given order? Right? For instance, what if we found a subgroup, right? So let's think about this a bit. So if Lagrange's theorem is saying that a group must have a given order, right? So suppose, right, in this particular case, in fact, right, so suppose we have a group, in this case we have what? We have G, right? Let's use M. Suppose we're being told we have a group whose order is, I don't know, P to the alpha times M, right? P to the alpha times M. At the moment we don't want to do that. Let's focus, let's be just a little more playful first. Suppose we have a group M, and when we take the order of M, it's finite, so can we write it as a product of prime? Suppose we write as product of prime and gives us, let's say, 5 times 3 times 2. Right? If we're saying that any subgroup L of M has the property that the order of L divides M, right, what are we saying that the only possible values of the order of L can be? Right? Can the order of L be 7, for instance? Does 7 divide the order of M if the order of M is 5 times 3 times 2? Okay. So if the order of L can't be 7, what are the possibilities for the order of L? Could the order of L be 1? Right. Right. Could it be 2, perhaps? Right. Does 2 divide order of M? How about 3? Does 3 divide order of M? How about 4? Does 4 divide order of M? What do you think? How about 5? Okay. So are we saying that if we know the prime factorization, if we know the factorization of a given group, then we know we can at least restrict the options of what the subgroups, the order of the subgroups can be. In this case, if it's 5, 3, 2, then are we saying that the only allowed orders are 1, 2, 3, and 5? Because 1, 2, 3, and 5 are the only things that divide the order of M, right? So could that be another approach, right? So maybe in this case we could just make it a little more specific here, but right, since we are being told that the order of G equals to P to the alpha times M, right? Since order of G equals to P to the alpha times M, can we say that, can we restrict order of H to divisors of P to the alpha times M? Suppose we restricted the order of H to divisors of P to the alpha times M. Would that give us, how would that help us? So if let's say we found all the divisors of H, all the divisors of M, and we wrote them down, maybe one of them is maybe one of them is beta 1, or the other divisor is beta 2, or all the way up to all the possible divisors. Let's say there are divisors of H, of P to the alpha times M, the order of G. Could we perhaps, like, maybe do some process of elimination, right? I mean, obviously, could we say that one of the divisors is going to be P to the alpha? Does P to the alpha divide P to the alpha times M? So maybe let's write this in a much cleaner way, right? So we don't want to get carried away here. So no, we're saying order of G, if order of G equals to P to the alpha times M, right? Well, and given that, I mean, is order of G finite if order of G equals to P to the alpha times M? So can we perhaps find all the possible divisors of P to the, can we find all the possible divisors of P to the alpha times M? Because isn't Lagrange's theorem telling us that the order of every subgroup H of G must divide the order of G? So suppose we're able to find all the possible divisors of G, of P to the alpha times M. Couldn't we say that the order of G couldn't, let's say these were the divisors. Well, there's some divisor called beta 1, and another divisor called beta 2, or I don't know, beta 3, another divisor, or and so on and so forth. And maybe, do you think P to the alpha is a divisor of P to the alpha times M, or some other possibility, let's say up to beta to the R? What strategy now, given this information, that if we wrote down all the divisors and we know that order of H has to be one of the divisors, what's one possible strategy that may help us to solve this problem? Can you think of one? Suppose we show that the order of H cannot be beta 1, right? And suppose we show that the order of H cannot be beta 1, and the order of H cannot be beta 2, and the order of H cannot be beta 3. It cannot be any of the other possibilities, and it can't be any of the other possibilities. Wouldn't that necessarily tell us that the order of H now has to be P to the alpha, right? So maybe this is one strategy. We find a subgroup for which none of the other divisors work except for P to the alpha, right? So so how are we going to write that as a strategy? So let's go back to our strategy corner here. We're saying, look, maybe since order of G equals to P to the alpha times M, why not restrict order of H to divisors of P to the alpha times M and eliminate, right? Right, maybe eliminate. Maybe this is what will work for us. Perhaps we could just do elimination, all right? What's another possibility? Whether this will be hard or not, we are not sure yet. At the moment, it's not our concern. Right now, we are concerned with one task. Just figuring out as many ways as we possibly know of showing that a group has a subgroup of a given order, or that a certain group has a given order. Is there anything else you can think of? Is there any other way to show that a group has to have a certain order? Or in this particular case, just think about order of G. What about something called an isomorphism? So, not sure if you're familiar with an isomorphism, but suppose we show that the group G, sorry, that there exists a subgroup H of G such that H is isomorphic. We're going to explain what isomorphic means. Is isomorphic to Z mod P to the alpha Z. Right. So maybe this is a mouthful. What does this mean and why would that be helpful? Okay, so let's think about this. What's an isomorphism, right? Is the idea. What's an isomorphism? Right. So we're talking about isomorphic, right? Right. So isomorphic, I mean, you saw what we wrote there. We wrote that one kind of show that H is isomorphic to Z mod P to the alpha Z. What do you notice? Isn't this symbol here almost like an equality, except that perhaps we have a dash on the top, some squiggly line on the top? So is isomorphism related to equality? Well, very much so is what we're going to say. In fact, what we're really trying to capture is this idea. Well, what if we showed that H was pretty much the same, that in our group G we had a subgroup H of G, and this H was pretty much the same as Z to the P to the alpha Z. Okay, what do we mean by pretty much the same? Right. When we say pretty much the same, well, could we say this? Suppose we showed that when two groups are pretty much the same, or what we're calling isomorphic, suppose we're able to show that at least one thing that's true is that they must have the same size. Right? So order of H must equal to order of Z to the P to the alpha Z. Right? Suppose this was, let's say, we want to establish what it means for two groups to be the same. So if we have some group H, all right, and we have some other group, let's say we have some group N and we have another group K, and we are saying these things are isomorphic. That is, we're saying they're the same. What do we want to be true about them? Well, we want them to have, what kind of things do we want them to have in common, right? So would it be really cool to have the following property, that if two groups are isomorphic or they're kind of the same, it means that at least they have the same cardinality. Right. What else would you want? Would you want to say that, look, if one of them, if let's say there is some n in n such that order of n equals to, I don't know, r, if there's an element in n of order r, do we also want it to be true that that's true if and only if there is some element little k in k such that order of k equals to r? Right? Right. Would this be a nice notion of similarity, that if two groups are the same, if they are so isomorphic to each other, then they have the same size, and if one of them, if let's say n has an element of order, of some order, let's say n has an element of order 2, then k must also have an element of order 2. And if just another set of similarities maybe would be, well, look, in fact, the number of elements of some order, let's say if we have if we have 3 elements in n that have order 7, then we also want k to have 3 elements that have order 7, right, etc., etc. So why would this notion of similarity be of interest to us? Right? Let's think about it before we even think about what an isomorphism is, or before we decide if we even need to go there. So let's notice something, right? If we actually establish this notion of similarity, that is, we actually came up with a similarity that makes sense, and we're able to say that H is isomorphic to Z mod P to the alpha Z, right? It's the same as this group, Z mod P to the alpha Z. Well, what's the order of Z mod P to the alpha Z? Isn't the order of Z mod P to the alpha Z just P to the alpha, right? So this is the mod group. The assumption is that you're familiar with it. Z mod P to the alpha Z is just the set 0, 1, 2, all the way up till P to the alpha minus 1, where these things are being considered under addition and elements are being considered mod P to the alpha, right? So that's the mod group. Yeah, if you're confused, please check out, there's a video in this called mod group, right? Yeah, I think we made a video. So just look up Christian Mojaiso. There's on abstract algebra. There is a in the playlist of abstract algebra. There is a group we're calling the mod group, and this is what we're describing here. So we're looking at Z mod P to the alpha Z, right? So we're saying, well, what if H is actually the same or isomorphic to Z mod P to the alpha Z, right? If we can show this, well, can't we? What's the order of Z mod P to the alpha Z? How many elements are there? We have 0, 1, all the way to P to the alpha minus 1. So can we say that there are P to the alpha elements in Z mod P to the alpha Z? Okay. If there are P to the alpha elements in Z mod P to the alpha Z, and we are saying that if two groups are isomorphic, if they are the same, they must have the same size. Aren't we saying then that order of H must also be equal to P to the alpha? Right. So at the very least, suppose we are able to make sense of this isomorphism thing. If we're able to define clearly what it means for two groups to be the same, isomorphic to each other, if we showed that, well, there exists some subgroup H, suppose we prove that there exists some subgroup H of G such that order of H, such that H is isomorphic to Z mod P to the alpha Z, wouldn't we then have shown that order of H equals to P to the alpha? Right? So maybe this isomorphism idea may be useful to us. We're not sure yet, but it may be. So does it make sense why maybe we might want to put this idea on our chart here of possibilities, that there exists a subgroup H of G such that H is isomorphic, whatever isomorphic means, kind of the same to Z mod P to the alpha Z. Right? So at the moment we don't want to, this is isomorphic symbol. At the moment, maybe we don't want to go down this route because we are not sure yet if it's going to pan out or not, or if the other possibilities are going to pan out. So why spend time finding out what an isomorphism is when it may not help us to solve this particular problem? So let's first write down all our possibilities and then we'll proceed systematically. All right. What is the fourth possibility is the question. What's the fourth possibility? Is there any other way we can show that there is a subgroup of a given order, right? Let's see, are we running dry here? Do we have anything else? Okay, well, we notice that one thing also we're being told is that the order of the group G is actually equal to P to the alpha times M. Okay. And we're being told that the GCD of P and M is 1. That is, well, P and M have no factors in common. Alright, well, what if we proved that there is a subgroup, there exists some H subgroup of G such that order of H does not equal to M. Right. That is, we have a subgroup of G, its order is not M, and maybe we're saying, yeah, right, we're saying that, and maybe, I mean, we have one particular example. Isn't the identity a group? If the identity is a group, can its order equal to M if M is not 1, right? So let's say that we're always guaranteed a subgroup H, not necessarily non-identity, right? So maybe let's say, suppose you're always guaranteed that there exists some H which is non-trivial. That is, it's not the entire group, it's not the identity. Or at least it's definitely not the identity. That is, H not equal to, suppose we found some H that wasn't equal to the identity, was not equal to the identity group, right? And also we found that order of H does not equal to M, right? Given Lagrange's theorem and the fact that the order of every subgroup must divide the order of the group, that is, given that the order of every subgroup H must divide the order of the group, if we're saying, well, the order of H is not 1 and the order of H is not M, what possibilities does that leave us? What are the possible values of order of H? Right. What are the possible divisors if we're not allowed to use M at all? Well, maybe it's not M, but it may be, what could it be? Could the possibilities be P to the 0? Okay. Maybe this may not be as helpful. We don't know yet. But P to the 2, are those the possible divisors of P to the alpha times M, all the way up till P to the alpha? Or, I mean, we also have M times P, M times P1, M times P2. Okay. So this may be getting a little complex here, but maybe this approach may not help us. May not. We don't know yet. No element. Let's just write it there just in case, but it's unclear of what value this will be. Perhaps we could say that there exists some subgroup H of M, H of G, such that order of H does not equal to M, or is not, maybe figure out the relation between the order of H and M. Okay, figure out how is order of H related to M, to order of M equals to P to the alpha times M. Well, I mean, one might say, isn't this the whole point of the problem? Okay, so we're going to put a star on this strategy. We're not even sure if it's a strategy at all. Alright, yeah, so we've just run through some possibilities. It's hard to think of anything else. Actually, how do we know it's hard if we haven't tried? Can we think of anything else that... Right, and we also run out of time. So far, why don't we delve into these 4 strategies and see what they give us? Let's see if we could think of anything else, any other strategy that may solve this problem for us. Yeah, it's hard to... can't think of anything. How else would we show that a group has a certain order, or that a group has order P to the alpha in particular? Well, we do have one more tool at our disposal. So again, in the Lagrange's theorem video, we proved the following. We proved that, and again, you shouldn't take our word for it. Please try and figure it out, or at least watch the videos in exploration of Lagrange's theorem. So that's exploration of Lagrange's theorem. The French guy again, Lagrange. This is A-N-G-E-S, Lagrange's theorem. I think this was maybe either 14 or 15, right? We're not sure yet, but we came up with the following conclusion. If order of G if we have a group and the order of the group equals to p to the alpha, where alpha, p is prime and alpha is, let's say, greater than or equal to 1 at least, around there, well, we were able to prove that this implies that there exists some subgroup h of g such that order of h equals to p. So if we have a group of order p to the alpha, then we are guaranteed a subgroup of order p. Right? So maybe this will be useful to us in Sylows theorem. Maybe next time let's think about how could we use this theorem. It seems so related. Because here Sylows theorem is saying we have a group G of order p to the alpha times m, kind of similar to p to the alpha, and we are still trying to show that there exists some subgroup h of g, but the order of h is not being taken to be p, rather it's being taken to be p to the alpha. So in what way are these two things related? Let's think about that. Maybe this theorem here, right, guaranteeing a subgroup of order p may be useful to us. Right? So alright, so let's think about maybe how we could do this. How we could combine all this information to give us a subgroup, to prove Sylows theorem. But otherwise, thank you very much for watching this video. See if you can prove this theorem of Sylows. And yeah, well, yeah, have a relentless week. Bye.